Hello friends, welcome to a lecture series on essential mathematics for machine learning. So, however, we have seen analytical methods to solve our nonlinear problems. We have seen if a problem is a convex optimization problem, then the KKT conditions become sufficient. We can write the KKT condition and solve a problem, a nonlinear problem. Now, always analytic methods may not work because of the complexity of the problem, because the problems are not convex, or because of some other reason. So, we have some such techniques, numerical such techniques to handle such problems. So, this lecture is basically devoted to numerical optimization algorithms, that what numerical optimization algorithm which are useful in machine learning. So, first let us understand if you are having an unconstrained optimization problem. We have already discussed what unconstrained means. Unconstrained means without any constraint, without any restrictions. So, that means we have to simply minimize f x subject to x belongs to R n. If we have this problem and we want to minimize it, so the question arises, how can you find a point x bar in R n which solves the problem P, or at least approximately solve the problem P? Because in general our analytical approach may not work for all types of optimization problems. So, we move to search techniques or numerical optimization algorithms. So, what is the basic scheme? See, the basic scheme of any algorithm, of any numerical algorithm is, we have a current point x k, a direction d k. From x k there are so many directions. Say if you are having a point x k, from this x k there are infinite directions, okay, in which direction we should move. So, that direction is basically d k, the optimal direction. Alpha k is a step size, optimal step size, and using this relation the next iteration x k plus 1, which is equal to x k plus alpha k d k, the next iteration x k plus 1 can be found. So, here x k is a current solution, d k is a direction of movement from x k, and alpha k is a step size, the distance up to which we move from x k in the direction of d k to obtain x k plus 1. Okay. Now, how to find alpha k and d k? This alpha k and d k, these are not known to us, only x k, the current solution, is known to us. How can you find alpha k and d k such that we get x k plus 1 from x k in an efficient way? Okay. So, this is the next question. So, if we are having a minimization type problem, as we have discussed here, the minimization type problem, then we have descent property. What is descent property? See, if we are moving from a current solution x k to x k plus 1 such that the value of f at x k plus 1 is less than value of f at x k, that means we are going in a descent direction. If it is a maximization type and f at x k plus 1 is more than f at x k, then we say that it is an ascent direction. Okay. So, an algorithm for solving P is said to have a descent property if this inequality holds for every k, and that is as we proceed the value of objective function decreases. Now, if we are developing any algorithm, any numerical algorithm, so we have certain terms related to that algorithm. First is order of convergence. What is the order of convergence of that algorithm? So, how we define order of convergence? So, let us sequence x k converges to a point x bar, okay, and let x k is not equal to x bar for sufficiently large k. The quantity, the norm of x k minus x bar is called the error of the kth iteration, of course, because x k converges to x bar, and the norm of x k minus x bar, because we have to anyhow approach to x k. So, this is nothing but the error term at the kth iteration. Suppose there exists a p and alpha in between 0 and infinity such that norm of x k plus 1 minus x bar divided by norm of x k minus x bar whole raised to power p, as limit k tends to infinity if it is alpha, then P is called order of convergence of sequence xk. That means this value must be finite. If this value is finite for some p, then that p is called order of convergence of sequence xk. Okay. Now, if p equal to 1, if for some algorithm the sequence x1, x2, x3 up to xk and so on, if that sequence converges for p equal to 1, then we say that the sequence is linearly convergent. Okay. If in this p comes out to be 1, that means that sequence is linearly convergent. If p equal to 2, then we say the sequence is quadratic convergent or convergent of order 2. Of course, the larger value of p, what indicates the larger value of p? If you are having p 3, p 3.5 or something for some algorithms, that means the algorithm is faster. The larger value of p indicates the faster the algorithm will converge. Okay. Now, we are having unimodal function. What do you mean by unimodal function? The function f from an interval a b. Now, this initial interval is called interval of uncertainty. See, you are having a closed interval a b and you are interested to find out point x, which is the optimal solution of a given unconstrained optimization problem. So, this initial interval is called interval of uncertainty. So, this problem, the function from a b to r is said to be unimodal function if it has only one peak in the given interval a b. Okay. If it is only one peak, either minima or maxima, only one peak is called unimodal function. Let us suppose you are having a unimodal minimum function f from a b to r, then there exists x between a and b such that, see, if you are having a unimodal function, if you are having a unimodal minimum function, okay. So, it may be of this type, it is only one peak. So, it is unimodal minimum and minimum also. So, it is unimodal minimum function. So, if you are saying that this is a initial interval of uncertainty a b, if you are saying that this is the initial interval of uncertainty a b, then this is a closed interval a b. So, these points are also inclusive. Then that means that it first decreases up to some point and then increases, because it is a unimodal minimum function. So, that is what I have stated here, that first of all there will be a x in between a and b, and that x is the minimum point, where it first strictly decreases from a to x and then increases from x to b. Similarly, we can define unimodal minimum maximum function. Now, in unimodal minimum functions, the various cases may arise. So, let us discuss these cases now. Suppose you are having in between a and b, you are having two experiments x1 and x2. Okay. So, this is y equal to f x, a function. Okay. This is a and this is some point b. This is the initial interval of uncertainty a b. Now, you are having two experiments here. Now, the 2 point x1 x2 may be anywhere in between a and b, and let us suppose x1 is less than x2 and between a and b. So, let us suppose x1 is here and suppose x2 is here. So, in this case f x1 is more than f x2, because this height is more than this height. So, where does maximum belongs to? It implies x minimum will belongs to which interval? See, this x minimum is somewhat here. Okay. Now, this x2 may be here also, this x2 may be here also. So, we can say because this is f x1 is less than f x2. So, this point may be here also. So, we can say that this belongs to x1 to b, because x1 cannot be here. If x1 is here, because x1 is less than x2, and if x1 is here, here it is increasing. So, this inequality will not hold. Okay. Now, the second case which may arise is, this is A, this is B. The second case which may arise is x 1 is somewhat here and x 2 is somewhat here. That means f x 1 is less than f x 2. So, x minimum belongs to in which interval? C. Now, x 1 is less than x 2. So, this x 1 may be here also, okay. But this x 2 cannot be here because x 1 is less than x 2. So, we can say that minimum always belongs to a to x 2 in any case, whether x 1 is here or here, minimum always belongs to a to x 2. So, this is the second case, case 2. Now, what is the case 3? Case 3, it may be that you are having unimodal minimum function like this. This is the point A, this is the point B, and the two experiments which you have found x 1 and x 2, you are having two experiments such that f x 1 is equal to f x 2. Okay. So, you will be having only three cases, either f x 1 will be less than f x 2, or f x 1 will be more than f x 2, or f x 1 equal to f x 2. If it is equation, then this implies x minimum will belongs to, of course, in between x 1 and x 2. Okay, x minimum is here, somewhat here. So, that is basically unimodal function. So, if we are dealing with a unimodal function and we are finding experiments by any method, then either these three cases may arise. So, if you have a unimodal function, by any experiments you find experiments x 1 and x 2, then each time you are reducing the size of the experiment. Okay. See, if x 1 and x 2 are like this, that f x 1 is less than f x 2, then x minimum will belong to this. Then that means now the new interval of uncertainty is a to x 2 instead of a to b, and then you will perform the same method on this interval, and if again it comes out to be this, then again the size of the interval will decrease and the process proceed, continue till you get the required accuracy. Now, how we can find out measure of effectiveness of an algorithm? So, that will be simply given by width of the nth interval of uncertainty divided by initial width of uncertainty. So, that is basically alpha, and this alpha is always less than 1. So, this is how we can define measure of effectiveness. Now, let us come to the first method, which is steepest descent method. Now, what is steepest descent method? See, suppose you are having an unconstrained optimization problem of this type, minimization of f x, x belongs to R n, where f has continuous first order partial derivatives in R n. Okay. Now, what is the numerical algorithm? The algorithm is, you first choose a starting point as x 1. We can take a point, initial point as x 1 or initial guess as x 1, and move toward the optimal point according to the following rule. So, rule is the same rule which we have discussed initially, that x k plus 1 is x k plus, here alpha, initial alpha k you are having lambda k d k. Now, d k is a direction, and here is a minimization type problem. So, that direction must have descent property. Descent property means that f of x k plus 1 should be less than f at x k, and lambda k is the optimal step size which can be obtained by this. So, how we will obtain this, let us discuss. So, first of all in steepest descent method, this point is x k. Okay. It may be x 1, x 2 or any point. From this x k, as we already discussed, there are infinite direction. In which direction we should move? That is the first thing. Now, it is a minimization type problem, okay, and we know that the rate of change of a function decreases most rapidly if we move along negative of gradient of f. Okay. So, that means if we move along negative of gradient of f at this point x k and take that as a descent direction. So, that will definitely the direction where the value of the f decreases. Now, the question is how we can find out the optimal step size. See, we have find a direction dk which is nothing but negative of gradient of f at x k, okay, and x k plus 1 is nothing but x k plus lambda k dk. Now, this d alpha k is nothing but this alpha k is c from here we have to reach a point x k plus 1 and this is the step size. So, how we can find out the optimal step size? So, if we put this x k plus 1, this f of x k plus 1 and if we minimize this over lambda k, then this will give the optimal step size. Okay. So, let us discuss it by an example. First, we will see few properties of this and what is stopping rule, up to how much we have to perform these iterations. We first start with x 1, then find x 2, x 3 and so on. So, the stopping rule is either norm of gradient of f x k should be less than epsilon, epsilon is a tolerance level which will be given to you, or the difference of the two successive iterations, the value of f at a two successive iterations, the norm of this should be less than epsilon dash. That is the stopping rule. Now, what are the properties of this method? The first property is it is globally convergent. Okay. The second property is it has order of convergence unity, that is p equal to 1 for this case, and it has a descent property. Of course, it has a descent property, that means f of x k plus 1 is less than f x k for all k. So, that is an important property and it is very easy to understand, easy to apply, that is why we are using this algorithm in machine learning. So, let us discuss this method by a example. Suppose you want to minimize this function x 1 square minus x 1 x 2 plus x 2 square such that we want that the difference of two consecutive values should be less than 0.05 and it is given to us that initial gas as 1 and half. So, what is the problem? Problem is minimization of f which is equal to x 1 square minus x 1 x 2 plus x 2 square. This is the problem. Okay. So, what is the initial gas? Initial gas is 1 comma 1 by 2 half. So, first let us find gradient of f. So, what is gradient of f? Gradient of f is 2 x 1 minus x 2, here it is minus x 1 plus 2 x 2 whole transpose. So, this will be gradient of f. Now, what is gradient of f at x 1? At initial case x 1. So, put x 1 equal to 1 and x 2 equal to half. So, 2 minus half is 3 by 2 and it is 1 by 2. So, that is 0. So, it is 0 transpose. So, this will be gradient of f. Okay. Now, what will be d1? d1 is nothing but negative of gradient of f x 1 and that will be nothing but minus 3 by 2 and 0 transpose. Okay. So, the x 2 from the steepest descent method by the recursive algorithm, that will be nothing but x 1 plus alpha 1 or lambda 1 d 1, that will be nothing but x 1 plus alpha 1 times minus 3 by 2 comma 0. So, that is this transpose. So, what is x 1? X 1 is 1 by 2 transpose plus alpha 1 minus 3 by 2 0 whole transpose. So, that will be 1 minus 3 by 2 alpha 1 and 1 by 2. So, that will be x 2. Now, how to find x 2? You simply substitute this point in this function and now it will be a function of single variable alpha 1 and try to minimize that function. we have to find out alpha 1 for which that f is minimum. So, simply substitute this over here. So, let us try to find out. So, what is f x 2? F x 2 will be, f x 2 is you replace here, you replace x 1 by 1 minus 3 by 2 alpha 1. So, you replace x 1 by 1 minus 3 by 2 alpha 1 whole square minus 1 minus 3 by 2 alpha 1, and x 2 is what? X 2 is half. So, it is half and plus 1 by 4. So, now it is a function of single variable alpha 1. So, you differentiate respect to alpha 1 and put it equal to 0 for maxima and minima. So, it will be 2 times 1 minus 3 by 2 alpha 1 minus 3 by 2 minus minus plus 3 by 4 and put it equal to 0. Second derivative is, of course, second derivative here is positive, that means minima. Second derivative with respect to alpha 1 is positive, that means minima. Okay. So, let us compute alpha 1 from here. So, 2 cancels out. So, it is nothing but minus 3, and it is plus 9 by 2 alpha 1 plus 3 by 4 equal to 0. So, that will be this implies 9 by 2 alpha 1 should be equal to 3 minus 3 by 4. So, it is 12 minus 3, that is 9. So, it is 9 by 4 alpha 1. So, this 9 by 4. So, this is simply 9 by 4, and this imply alpha 1 is 1 by 2. So, in this way we obtain alpha 1. So, what will be x 1 x 2 now? So, x 2 is nothing but, now I substitute alpha 1 here. Alpha 1 is what? 1 by 4. So, 1 by 4, that means it is 1 by 4 and half. So, it is 1 by 4 and half whole transpose. So, this is x 2. Now, we will compute f x 2 minus f x 1 and its norm or modulus. We will see whether this value is less than 0.05 or not, because that is a stopping rule here, that is a stopping rule here. If this is come out to be less than 0.05, that means we will take x 2 as the approximate solution of this given problem. So, what is this value? So, now we will see here. So, we have I have shown for x 2, and you can verify that f x 2 minus f x 1 is 0.75, which is not less than 0.05. So, hence this means we have to proceed further. So, in the same way we will find x 3 now. Now, x 3 will be given as x 2 plus alpha 2 d 2, alpha 2 or lambda 2, both are okay. So, lambda 2 d 2, x 2 is what? X 2 from here is 1 by 4 1 by 2. So, you can substitute x 2 as 1 by 4 1 by 2, lambda 2 is lambda 2, and d 2, how you will find d 2? D 2 is nothing but negative of gradient of f at x 2. So, gradient of f we have already computed, gradient of f is this. So, you have to find now gradient of f at x 2, x 2 is 1 by 2 1 by 4 1 by 2. So, you substitute x 1 as 1 by 4 and x 2 is 1 by 2, and find out gradient of f at x 2 at this point. So, we will obtain this. Okay. Now, again we substitute this x 3 in the function and try to minimize, try to find out that lambda 2 for which f is minimum, and after solving again we will get lambda 2 as half. So, when you substitute lambda 2 equal to half here, we will get x 3 as 1 by 4 1 by 8. Okay. And now, if you find out the mod of f x 3 minus f x 4, it comes out to be 9 by 64, which is less than 0.05. Now, we will stop here and we will say that x 3 is the approximate optimal solution of the given problem. So, in this way we have seen that if we are having a non-linear unconstrained optimization problem, then using a steepest descent method we can find out at least approximate optimal solution of a given problem. In the next lecture, we will see some more numerical search techniques for solving constraint optimization problems. Thank you.